In the final part of this course, we will take a closer look at the phenomenon of quantum tunneling. Previously, we encountered this phenomenon while examining the scattering of a quantum particle at a potential step. Now, we will explore tunneling in a more traditional context, where a quantum particle traverses a classically impenetrable potential barrier. To this end, we will examine a particle in one-dimensional space, along the x-axis, encountering a rectangular potential barrier. More precisely, the potential function is defined as follows. The potential equals a positive constant v sub 0 when x is between -a, and it is 0 for all other values of x. Thus, the height of the potential barrier is v sub 0, and its width is 2a. In the following discussion, it will be convenient to express the height of the barrier using a positive parameter alpha. Specifically, v sub 0 is given by h bar squared times alpha squared, divided by twice the particle's mass. Here, alpha has the dimensions of a wave vector, which is inverse length. Now, let's imagine a quantum particle, described by a localized wave packet, approaching the barrier from the left. We will focus only on wave packets whose energy is lower than the barrier height. Our goal is to predict the time evolution of such a wave packet during and after its interaction with the barrier. Notably, we will discover that there is a non-zero probability for the particle to pass through the barrier, illustrating the classically impossible phenomenon of quantum tunneling. We already know the general form of the spatiotemporal wave function describing the particle. It is the same expression as before, with one important modification. The upper integration limit is set to alpha instead of infinity. This change ensures that the particle's wave packet is a superposition of only those stationary states (psi), whose energy does not exceed the height of the barrier. As before, the function (psi) of x is found by solving the time-independent Schrödinger equation with the potential function v of x. The wave vector k is related to the energy E in the usual manner. Solving the Schrödinger equation is left as an exercise, with the complete solution provided in the accompanying notes. Here, I will outline only the key steps of the solution. The potential function divides the x-axis into three regions. We need to solve the Schrödinger equation separately in each of these regions. As mentioned earlier, we are only concerned with energies E that are below the barrier height v sub 0, which is equivalent to values of k that are smaller than alpha. A classical particle approaching the barrier from the left, with energy lower than the barrier height, cannot pass through it and will inevitably be reflected. In the incident region, to the left of -a, the Schrödinger equation assumes the free particle form, and its solution is a linear combination of the incident and reflected plane waves. The amplitude of the reflected wave is denoted by b. In the region under the barrier, between -a and a, the solution to the Schrödinger equation is a linear combination of two real exponentials. The growing exponential, e to the power of k prime x, and the decaying exponential, e to the power of -k prime x. Here, k prime is the square root of alpha squared minus k squared. The amplitudes of these exponentials are denoted by c and d. Finally, in the transmission region to the right of a, there is only a right-moving plane wave with wave vector k. Its amplitude is denoted by f. The function psi presented here has four complex-valued parameters, b, c, d, and f, that remain to be determined. These parameters are found by ensuring that psi is smooth across the entire x-axis. In other words, b, c, d, and f must be chosen so that psi is continuous and differentiable at x equal to -a and a. I won't provide the final answer here, as the expressions are quite lengthy. You can find it by working through the exercises, or it is available in the provided solutions. The key point, however, is that the amplitude f of the transmitted plane wave is generally non-zero. The superposition of transmitted plane waves with different values of k results in a localized right-moving wave packet in the transmission region, indicating a finite probability for the particle to tunnel through the barrier. Let's observe the tunneling process in action. We choose the function phi of k so that the initial wave packet is approximately Gaussian. Achieving a perfectly Gaussian wave packet is impossible because we use only a finite momentum range to construct the wave function psi. By design, the wave packet's energy is lower than the barrier height. Nevertheless, upon interacting with the barrier, a significant portion of the wave packet passes through it. This is quantum tunneling. The area under the transmitted part of the probability density gives the tunneling probability.